record on this. All right, welcome everyone. This is going to be our second lecture in data structures and algorithms. In this lecture, we're going to talk about big O notation. We talked a little bit about it during, or I believe you guys talked a little bit about it during your binary versus simple search conversation and why it's more effective. But today we're going to go into explaining big O notation, how to read it, what it stands for, and how to actually interpret these logarithms, and then into reading some problems and seeing what those problems actually are in big O notation. So the first thing we're going to tackle is, what is big O notation and what is it used for? So big O notation is essentially just the way that we analyze algorithms in order to determine their efficiency in returning a solution. All right, so there's two different types of efficiencies. And for those of you who have utilized LeetCode, you'll know that there is memory and then there is performance, right? Those two are separated whenever you're talking about how to solve an algorithm. And big O notation is specifically related to performance. So there's this handy dandy diagram here that I really like to show, and essentially just dives into how big O notation works, right? So we have O of n, which is just as the input increases, so n usually stands for input. As the input increases, so does the time to come up with a solution. Then we have n log of n, which is, it's not necessarily the worst, but it's not optimal. N log of n is actually pretty impressive. I've seen it being implemented in algorithms where, you think you have to utilize like 2 or 3 nested loops, and then someone comes up with a solution to get it to work in n log of n, and that is fantastic. So n log of n is usually the goal for more complicated algorithms. Something like a search algorithm, you probably want something like O log of n, right? Where we're implementing binary search, and that just means that is a divide and conquer algorithm. So O log of n. We're going to break these down later on, and as we see different problems. Again, n stands for the number of input, and you could see that pretty much as you continue going, it gets worse and worse. So this one, just as the input becomes less, the more time it will take to come up with the solution. So here's our horrible. We have fair, then we have good, and then we have our excellent, which is O log of n, or O of 1. All right. So now let's go into how to read these logarithmic expressions. So logarithms are actually pretty, let's see, when's the last time we did logarithms? I think you learn them in algebra in high school, I want to say, either there or geometry, one of the two. I can't remember off the top of my head, but definitely one of those old mathematical concepts that we haven't touched in a while. So let's go into what that means. So in the example where we have log of, oh, and I apologize, I should specify that log, we will always assume that it will be log of 2. So in the case that we have log of 2 of 16, well, that would equal 2, 4. All right, so let's go ahead and make this log of 2. And if this was by 16, this would be equal to 4. Now, how do we come up with that solution? Essentially, what log stands for is how many times will this number here on the right-hand side have to multiply itself to be able to go into 16. So if we take a look at 2 times 2, well, that would return 4, all right? If we multiply that times 2, that would return 8. And then if we multiply that times 2 one more time, we have our magical number of 16. So right now, if we execute Python main.py, we'll get that number of 16. So in total, we had to multiply 2 4 times to be able to achieve 16. All right. So now my question is, if we have log of 2 for 128, what would that be? Or what would that return?
7.
All right, so we're gonna go with 7 here. Oh, hello. My keyboard shortcuts are back, but apparently my keyboard skills aren't. So let's go ahead and add an extra 2 here to make it equal to 5. And let's execute python main.py. So that gave us 32. We multiply that times 2. That gives us 64. And then we multiply that times 2 for a total of 7. And that gives us 128. So we multiplied 2 by itself. So 2 to the power of 7 is equal to 128. All right. Does anyone have any questions about logarithms, how they work, and their implementation? No questions. All right. I'm feeling left out with these lack of questions. I'm not going to lie to you all. All right. So now we established how logarithms work, and in big O notation, we're always going to assume that log is equal to the root of 2. So log of 2n. This is essentially saying n log of 2n, and n stands for the number of inputs, right? Well, how do we determine where exactly our algorithm falls into place? So, for example, if I have a function, which is just a simple search that takes in a list of nums, and actually I'll do it this way, list. And returns an integer, which is the index where it's located. And all I do is say for x in LST, and actually let's include our second argument here. So let's say target, and let's have target be an integer as well. If x is equal to target, then return x. And if it goes to the entire list and it doesn't find something, then it'll just return -1. So there's our simple search. How do I determine where in this logarithmic expression or where in this big O complexity chart this simple search would fit in? Can anybody think of any ideas?
It would fall in the yellow since it's linear. So the bigger the integer or the longer the list, it'll always move at a linear pace.
Awesome. Yeah. So oh, and I see a question here from Jacob. Let's hear it.
Oh, it's pretty much the same thing as Demi, but does it have anything to do with? I also was wondering, does it have anything to do with how many lines of code are within the function? Like the more lines of code, like say for like a for loop, like I think I remember learning that in school. I'm not sure, but I remember there was something where it was just like each line or whatever can kind of determine if it's log of n or like just n in big O notation. I don't know if that has anything to do with it. I could be wrong, but
Yeah, that's a great question. So for lines of code, or LOC is usually how we measure projects or how we measure the size of memory that an algorithm or a project would take. It's typically referenced to as LOC, which is lines of code. So this in memory wise, it is not very efficient memory wise, right? But performance wise, which relates to Big O notation, we'll see that those two kind of don't agree with one another, right? Memory wise. So for example, if we take a look at something like a binary search is definitely way more lines of code than a simple search, right? And because of that, if you look at the memory performance, it'll say that a binary search is actually less efficient. But if you
okay.
look at the performance of the algorithm, it comes up in a better big O complexity.
Okay. Thank you.
Of course. All right. So simple search, just like we were talking about, right? It is by the number of inputs. So if I were to return, let's actually call this function. And let's say that we're going to pass in a list, which is just the range of 0 and let's go with 1000. But my target is 0. All right, and let's print that out. Well, that returned it pretty quickly and right away, right? It just returned 0. And right now, my algorithm, it essentially didn't iterate through the entire list. It just went into the very first index, and the very first index, it found the answer and returned and killed my function. So technically speaking, is this still O of n or is it now O of 1?
O of n because we measure by the worst case scenario.
Awesome. All right. Juan hit it right on the head, right? We are measuring by the worst case scenario that this algorithm could perform in. Yes, in this example, we are in O of 1, but that is just one scenario of the many applications that could come through here, right? If I was looking for 999 and then I search it, well, there's really no way to visualize it because Python is very efficient and our machine is also very efficient, but it would essentially have to iterate through the entire list. Once it goes into the final target, or yeah, once it goes into the final index, then it returns our actual answer, right? So there's a little bit of an issue there, and we could even do something like this so that we could see a little bit of difference in our outputs. You can see that it's at index 999. 4x in LST, and actually it's my code that is wrong. Let me fix that. It's just returning the number. There you go. Now it's working properly. I made a mistake in my code. I apologize, everyone. So now I'm returning my index. Once it hits that correct target, it returns the index. Great. So in the worst scenario, it had to iterate through the entire list. And as this list gets bigger, so if I just continue making my output larger, well, it's going to take longer, and you can actually see it now. It takes longer for the machine to be able to find the output, right? Whereas if I go back to, hey, I'm just looking for the number 1. Oh, wow, it's actually taking a while. And it returns 0, right? It takes a while because it has to build this list, I'm assuming. Not sure why it's taking so long in this case, but you can see that it took a longer time to actually be able to do the performance on the very last index versus the very first index. All right, so that's why we're staying at O of n. We are always evaluating by the very last number. All right, so now let's take a look at a couple of examples here. And I know this is kind of new, so I want to make sure that I emphasize this. As we go on through the cohort, you're going to see that our code starts kind of evolving. We're trying to emphasize that you shouldn't always maintain the same quality of code. You should always be trying to improve. This is called typecasting. This is not going to be enforced by Python in any way. It's something that you can do yourself to help you write code. In this case, I am establishing that I have a list of integers. That is the type that I'm utilizing here, which is a list. Here I have a target, which is an integer, and this function will return an integer. All right, and it's just something that I'm doing so that if I ever call this function later on in my program, I can get a couple of hints as to what parameters should go in there, what those parameter types should be, and what that function will return. It's just called typecasting. All right, now let's go into a concept such as constant time. So for constant time, we can do something very simple, such as accessing an element. And this function could just take in, again, a list, which is a simple list of integers. And, or maybe we could even make it a list of strings. And all we're doing here is we are taking an index, which is going to be an integer. And this is going to return list IDX. Now, I already said this is constant time. And can anybody explain to me why this is always going to be constant time and where in this big O complexity chart it would fall?
You're just
I think
picking
constant
one
time.
index, right?
Let me hear it, James.
You just grabbing one particular index, correct?
That's correct.
So it'll be
So
O over 1.
1.
Awesome. Yeah, it will be O of 1, just like James and Sam said, right? And it is always going to be O of 1 because I'm not iterating through any sort of string, regardless of the amount of input that I receive. It doesn't change my function, right? Like the input could be a massive list of range to 1001, or it could just be a simple list of 1 through 10. But it wouldn't change this algorithm's efficiency at all. It's just going to take in the list, take in an index, and have direct access to that index, right? So what other kind of data structure also allows for constant time or direct access?
Dictionary.
A dictionary, right? A dictionary will always allow key value pairs, which is a constant time access or direct access to an element. Fantastic. All right, so then there is linear time, which we've already covered, and let's go into something that would be O and log of n, which is going to be our binary search. Ooh, I haven't written a binary search in a while, so let's see how this goes. All right, so we have our list of integers. We have our target, which is an integer. This is going to return an int. And then we call our while loop where we say while, oh, that's not it. So we have our left, which is equal to 0, our right, which is equal to len list minus 1. And then we have our middle, which is right minus left. And that should all be in parentheses for division 2. Okay. Awesome. So now we run into our if statements. Oh, let me hear it, Juan.
Sorry, it was right plus left,
Thank you.
and then floor division. Yeah.
Right plus left and for division 2. All right. And then we could do a while loop saying while left is less than right. And check if list mid is equal to target. And if so, we will return mid. Else if list mid is greater than target. So if it's greater than the target, we want to return the left side. So the right side has to move. So then we would say right is equal to mid. Oh, hello.
Minus 1.
Oh, thank you. Minus 1. And then finally, else, where we have left is equal to mid, and I'm assuming this one would be plus 1. And then if it goes through that entire while loop and it doesn't work, then we'll return a -1. All right. Hopefully I did this right. Let's see how this goes. Let's go ahead and print our binary search here. And we're going to run our list here for a range of 1 to 100. And the number that we are looking for is, let's go with 99. right? Because that would be the, oh no, 100 would be the very last option. All right, so now if we execute this, I knew it. Let's see. Object of type integer has no len. Let's see, list of integers. Where are you raising this error, sir?
When
You
I
also
did
got to
this,
reassign the mid.
yeah. So I did my while loop, or I did my reassignment of mid in the while loop. And
Oh,
then yeah,
oh,
I did instead of typecast and list, I think I did it with array in my binary search as well.
I don't think it's my typecasting, is it? Oh man, let me go ahead and diagnose this real quick. No, mid doesn't exist until after. Let me run that one more time.
While mid does not equal the target, maybe.
No, it's definitely left is less than right. Well, we can see 49. The left is 0, the right is 99.
Also, I think it
Yeah,
has to be
Brandon just said it, but
less
yeah,
than or equal.
yeah, less than or equal in your while loop.
Well, that's, yeah. Oh, there you go. Yeah, now returns 99. Fantastic. Thank you. Appreciate it, Brandon. So while less than or equal to. Fantastic. All right. There you go. So there's our binary search. A little bit of a struggle bus, but we got it working. We have our left and our right, and we already covered how this goes into a divide and conquer algorithm, right? It's every time it iterates, it's dividing the list and making it smaller. So we could see an example here. For the first one, we have mid, which was 49. Then we have 0 being our left and our right being 99. Then all of a sudden we go into 74 for our middle, and now it's only searching between 50 and 99. Well, that didn't work, so it went to 87 for a middle, and it goes in between 75 and 99, then 93, and so on. And you can see that search is getting smaller and smaller, going from 5 numbers to 2 numbers, and then finally finding the answer and returning our answer. Right, so even though it's instead of iterating through this 100 times and finding our answer, it only did it 1, 2, 3, 4, 5, 6, 7, 8 times. All right, so that is why it is O log of n. And this is one of our other more efficient algorithms out there than log of 1, or excuse me, O of 1. All right. So far we've looked at linear time, constant time, and we've also taken a look at log of n. Does anyone have any questions over the 3 different algorithmic types that we just covered, how to read logarithms, or what big O notation is?
What was the three again? O of 1, O log of n, and what was the third?
So this one, binary search, is O log of n. We have this one for constant time, which is O of 1. And let me actually write that in there. And then we have our simple search, which is O of n. Does that answer your question, James? Okay, I see the head nods. Okay, fantastic. It doesn't seem like there are any other questions. So let's go ahead and take a break. Currently, it's 12 o'clock. Let's come back at 12, or excuse me, it's 2 o'clock for you guys. Let's come back at 2:10 and continue on with our lecture. All right. So far, we've seen O log of n. We've seen O of n, and we've seen O of 1. So we've seen all the good stuff, right? We've seen good, we've seen excellent, but we haven't necessarily seen bad. Now, bad falls into the whole quadratic thing. So let's take a look at horrible, and then after that, we'll take a look at bad. So this one is called bubble sort. Now, bubble sort is a sorting algorithm which essentially, and let's go ahead and typecast this as well, and returns a list of integers. All right, so what this does is it takes an n, which is just the length of the list. Once it has the length of the list, it starts iterating. So for idx in range of n, so we don't necessarily need n as of now. And then after that, it goes into for jdx in range of 0, n minus idx minus 1. This is all craziness. We're going to be diving deeper into bubble sort once we get into sorting algorithms. So don't try to decipher this entire thing as of now. And then we're going to ask, hey, if the list jdx is greater than list jdx plus 1. Nope, put that one on. Then we're going to take list jdx and list jdx plus 1. And what we're going to do is we're going to switch their values. All right, so we're going to make this jdx plus 1 and list jdx. All right, so all we're doing is doing a good old switcheroo here. So if we were to take a look at this in TL draw, what we would have is we have a list of pairs. Let me open this up here. Make that back to transparent. All right, so there's our list. Maybe we have just quickly fix all of these. All right, so maybe we have something like 2. Then we have something like 1. Here we have 5, 6. We have 3. And 4. All right, so it's going to iterate through the list. It's going to identify these 2 first. And it's going to say, hey, is 2 greater than 1? Well, they are. So let's switch their spots. All right, then it iterates through the list again. And it finds 5. Oh, well, 2 isn't greater than 5. So we don't care. Let's keep going. Then it finds 6. Okay, well, 5 isn't greater than 6. So I really don't care. Let's keep going. And then it goes to the next one. And it says, well, 3 is greater than 6. So let's switch those up. But because it did this switch, now it has to go through it all over again. All right, and it finds, hey, 1 is fine, 2 is okay, but 5 and 3, wait a minute, 5 is greater than 3. Let's switch those up. And then it switches them up again. And then it starts the whole array or the whole iteration all over again. Finds 1, 1 is good, brings down 2, okay, this pair is good, brings down 3, this pair is good, 5, this pair is good, 6 and 5, this pair is also good, but then it brings down 4. And it says, well, 4 and 6 aren't the same, so we have to switch them. And after it switches them, it restarts the entire iteration all over again. So now it takes 1 all over again, says, all right, well, 1 and 2 is good, Brings down 3, 2 and 3 is good. Brings down 5, 3 and 5 is good. And then it brings down 4, makes the switch. But after it makes the switch, it unfortunately makes the entire iteration another time. All right, so then finally it goes through the entire iteration and it finds that this is now organized. So it does what we want it to do and it accomplishes our goal, but it repeats this code so many times that it falls inside our O n log of n. Or excuse me, this is O n squared, which is quadratic, right? And a pretty simple way to identify if something is quadratic is the moment you see two for loops being nested inside of each other, that's a pretty good indicator of, hey, this is n squared, right? So O n squared is symbolized by two for loops, one nested within the other. So let's see it actually happening in action. And actually, let's just print the LST here. And at the end of it, we forgot to return LST. And let's see it here, actually, so we can see it for every iteration. So we're going to call our function. We're going to say print bubble sort. And we're going to pass that exact list that I had mentioned, which was 2, 1, 3, 5, 4. Oh, nope. And it was 6. And then it was 4. There you go. And all we wanted to do is for it to sort it. And we're going to see how many times this iteration goes through it, right? So it has to make a total number of, here's 1 flip and 2. It has to make 2 corrections in total. But because of the way the code is set up, we're going to see that it goes through way more iterations. All right, so there's 2 and 1. It does that automatic fix. Then it iterates all over again, finds 3 and 5 is good, goes all the way to 6. We can see that 4 gets switched between 6, but then it does the entire iteration again, and again, and again. Then it finally finds that switch, makes the switch between 4 and 5. And even though we now have a completed list and we no longer need to iterate through everything, we didn't have a way to kill it or kill the function to let it know, hey, we're good. Now that it's sorted, just return it. So it still goes through the entire process of iterating through the remaining of the list, even though it's already been ordered, and then it finally returns the ordered list. All right, and that's bubble sort in a nutshell. Again, we're going to go into it way more in depth later on, so please don't try to decipher it now. It's just important to clarify, if you see nested loops within one another, or if you're working in code and you have a nested loop, know that you have officially made a algorithm that is going to be n squared, O n squared. And that's not good, right? More than likely, you could refactor that algorithm to fall between O of n or O n log of n at the very minimum. Now, our very last example is merge sort, which is O n log of n. It's a pretty complicated algorithm, so I'm not going to dive. We're not going to be doing that today. We're going to save this algorithm until we go into sorting. And once we actually go into sorting and cover this in depth, then we'll be covering how that falls inside of O n log of n. But as of right now, that algorithm is definitely out of scope, so we're going to save it until then. All right, so today we covered constant time. We covered n squared, or excuse me, this is going to be n, where's my caret? There you are, squared, which is quadratic time. Here we have our O of 1, which is our constant time or our instant access. Then we have our O log of n, which is our binary search. We have our simple search, which is O of n. As the number of input increases, so does our time complexity to be able to find a solution. All right. Does anyone have any questions over any of the material that we covered today? No questions at all. So either I just cleared up big O like there's no tomorrow, or I left everybody so confused that you can't ask me a question. One of the two just happened, and I'm going to go with the latter.
Can you go a little more in depth on, I know you showed us on like on an actual display for bubble sort what's going on, but like the actual code of what's going on in bubble sort.
Oh, got it. Like breaking down the code.
Yeah, breaking down the code is. Thank you.
Absolutely. Yeah, so if we break down the code, we have n, which is just essentially representing the length of the list. So we can always change that. Oh, no, we can't. All right, so we have n, which is representing the length of the list. This is just an integer. We then create a range to the length of the list. The more typical thing that we see here is len lst, but because we're utilizing the length of the list later on, we save it as a variable. And then we have our first iteration, iterating through the entire list. And in the second iteration, we don't want to iterate through the entire list. We only want to iterate through a portion of the list or the working portion. So that's why we have this length of the list minus the current index minus 1. All right, so this way we don't fall out of index and we're staying within the scope that we want to work in. That print list, that's why we get that printed at the bottom. And then we're asking, hey, if the current number that I'm on, so if 1 is greater than 2 or 2 is greater than 1, let's say this is the example, then all I want you to do is I want you to do a variable reassignment, right? And that's where that's happening. I want you to reassign list index 1 as 1 and list index 2 as 2. And then we're going to return that to the list. And then it knocks into the next number. Once it finishes the entire list, so even though it's ordered, remember that first for loop is saying that it wants to iterate through the entire list. So it doesn't care when this is actually ordered. I could have a 0 to 1000 and maybe the only numbers messed up are here at the beginning. It's still going to iterate through the rest of those 1000 iterations, right? And for every single one of those 1000 iterations, it has an inner loop that it's iterating through as well, from start to the current index. Does that answer your question, Owen?
Yes, it does. I have another one after that. Or James, you go.
All right, let's hear it, James.
Yes, can you go back to line 38 and explain how you got range 0 and then you got n minus idx n minus 1.
Awesome. Yeah, let's go ahead and work through that. So the first iteration is asking, hey, I want to look through this entire list of 1 through 6. Well, my second iteration is saying, all right, well, you want to look through the entire list of this. But because we're doing bubble sort, I need to stay focused and only work with a couple of indexes. All right, so how do we fix this, right? Well, IDX is 0. So currently, the entire range is going to be looked at as well, -0 and -1. So in that next iteration, we're looking from 1 through 5. But what is there? What that is. All right, so -0. So n is the entire list, right? -0 and then -1, because when we start counting, we count by we count by 0. So that -1 just knocks us back into that number of 6, right? Yeah. And let me actually make this all smaller because as of right now, I'm having some trouble putting it all on the screen. All right. So there's that first of 4 JDX and -1. All right. So it goes through this, goes through the entire iteration. Then when it goes to the second loop, in that second loop, we're going through 2. Well, now we're saying, all right, we're going to take the entire length of the list, subtract 1, and then -1. So all we're doing is making the search between 1 through 5. the next iteration is 3, and then this closes this part. Next iteration is this way. They're essentially working opposite from each other. Does that answer your question there, James?
Yes, thank you.
Of course. All right. Any other questions? I think
Yeah,
you had
kind
another
of
one.
related to bubble sort, but it's still within the lines of algorithms. Say you have a dictionary of key, like obviously it has key value pairs, and some of those values are a list, and you want to return all of the key value pairs in that dictionary. And then obviously you need a nested for loop to get every value from that list. Is that still technically considered big O of n squared, or is that something a little different?
That's a great question. So that's goes into our or single responsibility principle, right? So what I would suggest if you have that scenario, and the scenario that we're talking about is something like, hey, I have a dictionary. This dictionary has multiple keys. In one of them, I have a list. And this list is just a range of numbers between, I don't know, 1 and 1,000, right? And I specifically wanted a specific number from this, and I wanted to know where inside of that index it is. Well, if I had multiple keys, let's say I have name, hello, and I had other thing, right? So what you're saying is I would want to iterate through these. I guess my first question is, why are you iterating through a dictionary? But let's talk about this scenario first. So one, I want to identify, maybe I don't know if list is located inside of this key, all right? Maybe I'm working with some sort of API that sometimes it returns this list and sometimes it doesn't. So one, I need to make sure that the list exists. So I would make a function saying, hey, does list exist? All right, and this would just take in a dictionary. And what this would do is it would return a Boolean of true or false. And I could iterate through the list. So for key in dictionary, if key is equal to list, return true. Right, there's definitely more effective ways to write this, but this is just to demonstrate that we're iterating through the list. Right, ideally we would do something like return key or if list in date, right? That would be the ideal scenario, but this works as well, right? So there's one iteration. And maybe for a second iteration, we do something like our binary search, right? Instead of having a whole function that would do that, we implement our binary search for finding target none. Well, this is still a loop, right? And it's still iterating, but notice how these two are broken up, right? So here we have a log of n, which is, excuse me, here we have an O of n, all right? And then here we have a O log of n. All right, well, they're separated from one another and they both have different efficiencies. But what happens if my function for accepting parameters, and I'm just naming these randomly, takes in a dictionary, right? And the first thing I do is I check if is present, and then I call my function of does list exists, and I pass in the dictionary. And then I say if is present, then I can call my finding target number, calling the dictionary list. And actually, let me clear that up there. And then I also pass in the number of, I don't know, let's say 35. All right. And then that would return an index, and I could return this. Well, finding a target number is still O log of n. This is still O of n, but this function isn't, right? This function is adopting both of those, and it kind of messes up their time complexity. It wouldn't fall into O n squared, but it also wouldn't fall inside of either of these, right? I would just assume that the worst scenario, because we're measuring by the worst scenario, is what would take over. So because thus list exists, it's O of n. That would make accepting parameters O of n. Does that answer your question, Owen?
It does. Yeah.
That was a whole rabbit hole. I apologize, everyone. All right. Any other questions? Okay, fantastic. I'm going to go ahead and stop our recording here.